It's space weather. Looking at the sun, 193 angstroms. We got one coronal hole rotating out and one coronal hole rotating in. And the wind stream from the former has arrived. We're going to talk about cosmic ray comparisons. We're going to talk about the most massive object in the universe. And more. Take a look at the sun in, what is it? 304 angstroms. We do see some pretty violent looking filament activity, especially on the eastern limb. And indeed there is some ejecta, some plasma filament ejection coming out of this area. It is a CME. It is not facing the Earth. Let's look at 171 angstroms. Some interesting magnetic field behavior going on. You can see how jumbled up all these loops are over here, which is probably why they're spewing plasma into space, as sunspot 2727 rotates out and appears to shrink down to nothing. Let's look at your magnetic lines. What are we at? 94 angstroms. You can see the northern portion of the sun is pretty normal. And the southern portion features a whole bunch of jumbled up magnetic fields. This coronal hole, you can see some real dense lines over here associated with sunspot 2727. Look at some spaceweathernews.com data. We've had a tiny X-ray flux, nothing even reaching into the B class since yesterday's update. And before we move on, let's look at the real-time solar wind. By the way, we will be leaving links to all of these sites below in the description. And here's your real-time solar wind. Looks like the BTBZ is finally converging and becoming a little bit less spiky. We did see a limited time of a phi angle around what was predicted there, around 130 or so. That was a coronal hole magnetic connection. Didn't last very long. We do see a recent downturn actually in solar wind density. We're down to 8.44 cubic centimeters. 8.44 protons per cubic centimeter. We've come down from 10. We were at about, looks like we were at about 15 or 20 there. And as we typically do see, we see before the coronal hole wind stream arrives, we see an uptick in density. And then at the same time, the speed increases as it has done here from about 325 to 434 kilometers per second. We see the solar wind density drop off as it just updated. We just actually saw it happen. We lost an entire proton per cubic centimeter there. Head back to spaceweathernews.com. The ACE and Discover are pretty much agreeing. We see some violent magnetometer spikes. This is associated with coronal holes connecting and disconnecting magnetically. And as the smaller coronal hole rotates toward the Earth, we're awaiting that connection probably within the next 12 hours. Although it's pretty hard to analyze it because the magnetic field from the larger coronal hole is masking the magnetic field from the incoming coronal hole. You can see the KP's been up to 3. Now we're back down to 1. So cosmic ray alert at a low level gets reinitiated, and we see the typical thing we see associated with coronal hole wind streams here. We see this drop off in the electron flux because protons love their electrons, and that's a standard thing we see regularly. Based on the time frames of this electron flux should be just about ready to pop back up now. F2 ionosphere layer is looking pretty normal. There's your auroral forecasts. We're going to go back a little longer than we normally do for earthquakes. Let's go back 10 hours to the last 5, second last 5. Anyway, we got a 5.0 magnitude in Tonga 10 hours ago, a 5.4 on Papua New Guinea, 5.3 in Indonesia, that whole area. One of the larger quakes in the Alaskan Peninsula here at a 4.7. And Peru gets hit with a 5.5. That's pretty bad news for Peru. That should have caused some damage. Although it was at 56 kilometers depth, which is better than being at the surface, obviously. Another 4.5 in northern Peru. So that seems to be a hot spot right now. And yeah, California, geez. Look at the number of quakes. Now, let's get into the stellar cosmological weeds. What's the most massive object in the universe? Well, first of all, you got to figure out what the definition of the term object is. But if you're going to use self-gravitationally bound objects as an object, you have to include galactic clusters. And this cluster here, known as SPT 2349, is currently the biggest object known in the universe. Why are we covering it? We're covering it because it's yet another observation that throws the standard cosmological model in the garbage. Maybe not in the garbage, but it sure questions it. So what's so significant about it? Well, so it's about 12.4 billion light years away, estimated, which means we're looking at an image 12.4 billion years old. What does that mean? That means that this massive structure would have had to have formed only about 1 billion years after the theoretical Big Bang. Well, we don't believe, well, standard cosmology doesn't believe that object's this massive. And this, this organized, you can see spiral galaxy, spiral galaxy, spiral galaxy, spiral galaxy. Standard cosmology states that you can barely form a star by that point in time. So why do we have the most massive object in the universe forming so long ago? It completely flies in the face of the Big Bang, the age of the universe, dark matter, and all the other nonsense that so many people believe. We'll be leaving links to all the articles. Here it is in, I believe that's in radio frequency. And so let me just see here. Right. According to standard cosmology, it wasn't until about 1 billion years, when the universe became fully ionized and transparent, that we see galaxies start appearing. So these clusters appear about 1.4 billion years after the theoretical idea that the Big Bang occurred. And it should have taken much, much longer for those to evolve. So, in any case, it was discovered in 2010. And it was unusual enough to warrant further investigation, so we got some more photos and realized how massive it is. There it is. The most massive object in the universe. SPT... what's it called? I can't even remember. SPT 2349, a galaxy cluster. Pretty interesting. Read the articles. Don't get your panties in a bunch about cosmology. Now, let's take a look at the difference in cosmic rays here. Here's the Athens Neutron Monitor Station. This is 1 month. It's a pretty good graph there. Not a significant trend. It's actually a slight downtrend over this period. Something like this. But barely a downtrend. Let's compare this to Antarctica. As we know, at the poles, a lot more cosmic rays show up, and there's a much bigger range of cosmic rays. So here you see the green graph is Antarctica DOMB, and the blue is the Athens Neutron Monitor. You can see what a massive difference it is at the poles versus, in Greece, a much more, what would you call it, a temperate zone. So you can see this massive range versus this tiny range. And that's because of charge separation, because of geomagnetism and so forth. One last thing here. I noticed there was some coronal mass ejections when I was looking at the LASCO C3. So let's have a look. By the way, this is Mercury, which is catching up to Earth. Now, if we zoom in on the left side, you can actually see some ejecta coming out in this direction. See some clouds coming out. Now, those are not facing the Earth. If they were, you would see what we call a halo. In other words, when a coronal mass ejection faces the Earth, you don't see it coming out like this. You see it coming out like this. You see it coming out like this. You see a cloud that grows in the center of the LASCO. In any case, that's how you can tell if a coronal mass ejection is facing the Earth. You can see these are all headed to the southeast. And that is today's space weather update. Thanks for tuning in, everybody. Thanks, subscribers. Please help us gain more subscribers by sharing with your friends on social media if you see fit. Please don't forget to like the videos. Leave a comment. Questions, concerns, constructive criticism, destructive criticism, straight up insults, death threats, whatever you want. Remember, when you're staring at the sun, don't drink. And if you drink, stare at the sun anyway. Use the SDO's 171 angstroms view. It's delightful.